Over 400 years ago, Galileo pointed a simple telescope toward the night sky and set his sights on the gas giant Jupiter. Imagine his excitement at the brilliant view. Hold on a second. This image of Jupiter is too detailed. That is definitely not what Galileo would have seen. His view was a little more minimal. This image is still too good compared to what Galileo saw, but it's at least closer. Anyway, with his small lens, Galileo became the first to observe Jupiter's moons, revealing a universe far more complex and dynamic than anyone had imagined. But Galileo's telescope could only capture visible light, the narrow band of light our eyes can see. Since then, telescopes have evolved into powerful instruments capable of detecting light our eyes can't, like the faint heat of infrared radiation or the energetic blasts of X-rays. Throughout this unit, light has been central to our exploration of the universe. It allowed Kepler to map planetary motion, revealed how gravity bends space in Einstein's theory, and helped us uncover the chemical makeup and properties of stars. Telescopes are the tools that capture starlight and transform it into the images and data used to answer our questions about the cosmos. But how did we get from Galileo's blurry view to the incredibly detailed and complex images we capture now? Let's dive into the remarkable world of telescopes, from massive ground-based observatories to space-based missions like Hubble, and find out. Galileo used a type of telescope known as a refracting telescope. His telescope worked by bending light through a curved glass lens. As light passed through the lens, it focused into a magnified image of the stars and planets. This allowed Galileo to see craters on the moon and discover 4 of Jupiter's moons, proving not everything in the universe orbits Earth. Refracting telescopes are still popular with amateur astronomers today, but they have limitations that make them less practical for modern scientific research. For example, refracting telescopes have a size limit. Glass lenses become heavy as they get bigger, making them difficult to mount without bending or warping under their own weight. And because different colors of light bend slightly differently through a lens, images can also become distorted, creating colorful halos around objects. Astronomers needed a clearer way to explore the universe. That's why the reflecting telescope was developed. Instead of using a lens to bend light, reflecting telescopes use a curved mirror to gather light and reflect it to a focus point. Why might using mirrors instead of lenses allow telescopes to be made larger? Unlike lenses, mirrors can be supported from underneath, preventing warping. This makes it possible to build much larger telescopes that can collect more light, allowing astronomers to see fainter, more distant objects. One of the most famous reflecting telescopes ever built is the Hubble Space Telescope, which has been orbiting Earth since 1990. Its giant mirror captures incredibly sharp images of galaxies, nebulae, and even planets in our own solar system, such as the detailed image of Jupiter we saw earlier. Today, reflecting telescopes have become the standard when trying to collect data from the visible, infrared, ultraviolet, or X-ray parts of the electromagnetic spectrum. But capturing light isn't just about the mechanics of the telescope. It also depends on where the telescope is located, whether here on Earth or high above the atmosphere in space. Imagine standing on a mountaintop, far from city lights, looking through a massive telescope pointed toward the night sky. This is what ground-based observatories do every night, capturing light from distant stars and galaxies. Telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile have enormous mirrors capable of gathering incredible amounts of light, allowing astronomers to see faint objects millions of light years away. Most ground based observatories are built in remote locations. Why do you think that is? Pause the video and make a prediction. It's because city lights create light pollution, which drowns out the faint light from distant stars. Secluded locations with clear, dark skies make it easier to capture the best possible images. But even in these isolated areas, there is a catch. The shifting air in Earth's atmosphere bends starlight, making stars appear to twinkle and blur through telescopes. The atmosphere itself distorts our view of the stars. To overcome this, ground telescopes use adaptive optics, a system that makes tiny adjustments to the telescope's mirrors to cancel out atmospheric distortion in real time, creating crystal clear images. But some of the universe's secrets can only be revealed by telescopes beyond our atmosphere. And that's why astronomers launched space-based telescopes like James Webb and Hubble. Orbiting far above Earth's atmosphere, these telescopes avoid blurring entirely and can detect types of light blocked from reaching the ground, like ultraviolet and infrared radiation. Hubble has captured breathtaking images of galaxies, nebulae, and planets like Jupiter for over 30 years. The James Webb Space Telescope, launched in 2021, specializes in infrared light, letting it peer even farther into the past to observe the first galaxies ever formed. Its advanced infrared sensors also reveal new details, like the ones in this image of Jupiter, showcasing the planet's storms and auroras in stunning clarity. Of course, operating in space has its own challenges. Repairs are incredibly difficult. When Hubble's mirror was discovered to be flawed, it took a space shuttle mission to fix it. Thankfully, the mission was a success, and Hubble has been delivering iconic images ever since. Both ground-based and space-based reflecting telescopes offer unique advantages, working together to help us explore the universe more fully. But to unlock the full spectrum of cosmic information, astronomers need even more specialized telescopes, like those designed to detect radio waves, X-rays, and gamma rays. So far, we've explored telescopes that capture visible light, ultraviolet, and infrared. But the universe holds even more mysteries. To study the most extreme cosmic events, astronomers use specialized telescopes designed to detect the highest and lowest energy forms of light. X-ray telescopes focus on some of the most energetic forms of light. Since X-rays can pass through most materials, standard mirrors don't work. Instead, these telescopes use special mirrors angled so the X-rays just skim their surface, like skipping stones on water. NASA's Chandra X-ray Observatory uses this design to study super hot gases around black holes, exploding stars, and the cores of distant galaxies. Gamma ray telescopes detect even more powerful radiation, gamma rays, the most energetic form of light in the universe. But gamma rays can't be focused with mirrors or lenses at all because they pass straight through most materials. Instead, telescopes like the Fermi Gamma Ray Space Telescope use particle detectors to measure the bursts of energy created when gamma rays interact with the telescope's sensors. Since Earth's atmosphere blocks gamma rays, telescopes like Fermi must operate from space, where they reveal events like black hole collisions, neutron star mergers, and massive supernova explosions. At the opposite end of the electromagnetic spectrum, radio telescopes detect light with much lower energy and longer wavelengths. These telescopes look very different from the telescopes we've explored so far. Instead of mirrors, they use large dish-shaped antennas to gather and focus radio waves onto a receiver. By linking many dishes together, astronomers can create detailed maps of galaxies, pulsars, and the remains of supernova explosions. For example, the Very Large Array in New Mexico, a group of radio dishes working together, was used to create detailed radio maps of Jupiter, revealing the movement of ammonia gas within Jupiter's atmosphere. These specialized telescopes expand our ability to explore the universe, bringing us closer to answering some of astronomy's biggest questions. By combining data from all of the different types of telescopes, astronomers can build a more complete picture of the universe, uncovering cosmic events and structures that would remain invisible if we relied on just one type. Excitingly, advancements are always being made. The next generation of telescopes promises to take us even farther in our exploration of the cosmos. You have the power to explore the cosmos too, whether through stargazing, learning more about telescopes, or even pursuing astronomy yourself. See you next time! Hey, hey.